Yeah. Yeah, we are live. Hi. Once again. Thank you all for joining this presentation. This session of presentations. Today we will listen to the presentations for the projects that were done in the Google Summer of Code for this CDLI project. I'm really happy about this because I think the projects were really good, and I'm very happy about the results, and I'm sure that a lot of you think the same way. We will start with machine translation presentation, which was done by Avneet. So please share your screen and start with your presentation.
Hello, am I audible?
Yes, we can hear you.
So let's start with the presentation. So hi everyone. So my project was on neural machine translation. So basically the organization was having a small data set of aligned Sumerian to English phrases. And the main aim of the project was to train a neural network based encoder decoder architecture to convert Sumerian to English phrases using machine translation technique, precisely neural machine translation technique, in order to support expert in cuneiform studies with automatic translation. So I was a student developer and Nico was my mentor. So in our overall project, what we completed is we basically explored the data set, we cleaned the data set. The data set was noisy, there were missing phrases and all. And then for training and testing purposes, we divide the data set into test train validation. The size of test train validation is 8,000, 10,000, 10,000 approximately. And we implemented a neural network based encoder decoder framework. So basically, we also experimented with different word embedding. We also experiment with pre-trained embedding from Wikipedia corpus, and we actually achieved better result from pre-trained embedding. So after this, coming to the architecture, we used two architecture. Basically, we implemented our own custom architecture, that is 2-layer encoder decoder model, and we also used a very famous architecture, that is transform model, that was given by Google in 2016, and it is a 6-layer encoder, 6-layer decoder. We will completely discuss it in further slides. So after the completing of this project, we are planning to publish a research paper on this, and if possible, we will add some command line interface to this. We also thought to add it by direction, like currently it's only Sumerian to English, but we are also planning to make it to English to Sumerian. So just a bit of history, how machine translation has evaluated during this time period. So around 1950, machine translation, computer used to translate the sentences from one language to another language. So from, as you can see on the screen, the RMBT, firstly, there is a rule-based machine translation that came to end in 1980. Then the example-based translation coming, and after 2015, the neural machine translation came into the light. That is our main project depends upon. So just a bit introduction how rule-based transaction were basically handwritten rules. We at that time we don't have that much computing power, only small written rules that was just meant to check spellings and just correcting the text, like basic text editing. Then example-based translation, this was the method. We add some more translation, like rule-based was checking the spellings. These can also check the grammatical forms, like adding vowels, etc. Statical translation machine, actually recently I also found a paper that CDLI has also produced the same project using statical machine translation. So basically it depends upon the probability. It check the probability in whole corpus, like this word should come into after this or not. This is also an quite old technique. And coming to our main project, that's it, neural machine translation. So coming to neural machine translation. So the ultimate goal of neural machine translation is to take a sentence as language as input and return the sentence as translated in different language as output. So with the power of deep learning, neural machine translation, uh, we have algorithms that can do this thing very easily and with a considerable results. We can't comment like actually no perfect system right now exists that can do it with 100% success. Even for well documented data set like English to German, we don't have still machines that can do it easily as a human. So before coming to algorithm, firstly we need a way to represent our words into machine readable formats. Machine only understand that like 0 and 1. So what basically we do is we use vectors. So like on this example, we can just, this is just a small example. So example, I only know 10 words. That is these are the list of words like a, the, red, orange, black, blue, white, etc. Like there's a language and only these 10 words exist in that language. So if I want to represent this sentence like the blue whale ate the fish, so what I will be doing is I will mapping this a 12 12 size vector, and when I will find the word the, I will add a 1 at this position and rest of the position will be 0. Similarly for blue, similarly for whale, similarly for 8 and red and fish. So this is how we make our machines to understand how our language is our language will be converted to machine readable format. After this coming, after representing our language, we need some relations. Like we don't we need to establish relation between words, like these words are matching, or like king and queen are kind of related, something like that. We need to basically establish some relation so we can perform various operations. So for this we use word embeddings. So word embeddings only allow the similar meanings to in a kind of vector space. So there are two most famous techniques. The first is word2vec. Word2vec was developed in 2013 to make and advance the research of neural network based translation. After 2013, after the invention of word2vec, neural machine translation technique evolved so much and taken over the statistical machine techniques. So basically how this word works is we use bag of word technique. So what bag of word technique does is it extract all the words from the corpus and then input it in a kind of vectors like the vector I showed previously, and then it use a summation operation, not the summation that we are thinking, it's a kind of different summation operation, and then we outputs another word vectors. Similarly, word2vec also can represent skip gram model. This is an n-gram model. So in n-gram model, we assume that a word is only related to its past few words. And then we have a pre-trained word embedding. That pre-trained word embedding is like this word2vec technique, we only establish the relations between the words we have in our data set. But of course, there will be such words that we didn't cover in our data set. Like our data set, for example, English to German, our data set consists of 100,000 lines. But in actual, there can be few words that also skip from that data set, and that is 100,000 lines. So to establish this, what we do is we made this kind of corpus using Wikipedia. So we assume that Wikipedia is a kind of place where we can found every word related to English, related to German, etc. There are other two versions too for this available. We can use this kind of corpus from Twitter, from Wikipedia, and from Reddit. I choose Wikipedia because we were doing a project on Sumerian to English. I don't think that there can be any word on Reddit or Twitter that is used on Sumerian, but we can found some articles on Wikipedia with related to Sumerian and English. So just for this reason, I use the Wikipedia corpus. So what we just do is we just make this kind of corpus from Wikipedia, and else we make these vectors again from our test and trained phrases. Suppose like this will be our training phrase, so we will be making this vector from this here. So after pre-training and making the embeddings, the next task was to design this kind of algorithm that will take the input phrase and give us output phrase. So for this, we use RNN, recurrent neural network, and long short memories. So assume that RNN is a kind of neuron. So explaining it like a neuron is, it's just store a number from 0 to 1. It is a double digit number and it's a 32-bit integer number. So to deciding its value, we use this kind of structure. So this is kind of complicated structure, and this is a representation of LSTM, how basically LSTM works look like. So this is a sigmoid function, and the equation of sigmoid is this 1 upon 1 plus e raised to power minus z. And we use these kind of 3-layer, and we use few summation, we use few multipliers, and we can see we give h of t as a input, xt as an input vector, and h of t is our output vector, and this is previous vector. So why we need this kind of structure is like we need to store the context of previous words. So when we will be building this kind of matrices, we assume that this blue will be related with this, and this red will be related with the a, whale, blue, and the. So we need to capture those word context. So that this structure is able to capture the previous vectors and the context with good results. I won't go much with mathematical expression. We will define this in our paper completely. And by using this a single, like this is just a single layer, I used this kind of encoder decoder. So every block of encoder is built by that structure, that is LSTM structure. And precisely I used 2-layer of encoder, like this is 2-layer of encoder. This is our word embedding, how where we previously defined the relationship. This is our vectors, and then things came into word embeddings where relation is established. And this is our kind of encoder that takes that are built using those LSTM structure. And in my sequence to sequence model, this is my custom model. I used 2 layers of encoder, 2 layers of decoder, and 512 neurons of each in layer. So using these encoder decoder, then we came to our decoder. And what this encoder uses deep neural transform. This deep neural network layer transform input words into corresponding hidden vectors. So this will be our hidden vector. And our decoder will be do similar things. It's take input as a hidden vector. This will be our hidden vector, and take input as a decoder, and then using again the embeddings. These embedding will be kind of different, but the function and evaluation will be a bit different, and we will get our desired input. So just in an overview, here we will give our input text. This will goes into word embeddings. Those embeddings will be passed through complicated LSTM units. Then they will generate a vector hidden layer, and that hidden layer will go into again decoder, and again using to decode the relationship, we use also embeddings, and we will get our desired sentence. So this was the thing, but the main problem is this LSTM has only kind of 3 sigmoid functions. So this is a kind of small sentence. A simple basic encoder decoder will be able to capture this. But suppose we have a sentence that is around like 50 words in that. So we will face issues in that. And the basic encoder structure perform very poorly with long sentences. So we need some attention mechanism. So these attention mechanism are kind of, so basically attention mechanism, just to give a simple overview, like the basic overview, what we do is the output of these encoder we will store in a layer. Like every output of encoder will be stored in an attention layer, and this attention layer will be fed as input to our decoder. So what we just change is we change this hidden layer with an attention layer, and some mathematical operation are of course backed by this attention layer to store all the context and all the data. So using this attention mechanism with encoder decoder, we achieved a blue score of 21 out of on a scale of 100. Then there is also, as I discussed, there is one famous transform model. So this came into light in 2016, and this model is kind of very sensitive model. So I didn't invent it. I just basically mimic the exact configuration to achieve some results. And with exacting, after mimicking the exact exacting parameters and all tunings, we basically achieved a results of 20 using this model. So this is kind of complicated figure how this transform model is used. And what this transform model is using, it is also containing, and this is kind of in encoder, and this is kind of decoder. So encoder is created by input embeddings layer, similarly in our sequence to sequence layer, but here our positional encoding also takes place. So position encoding is like they map the positions in a 3D space, how things are going to related, how it is basically representing those vectors in 3D space. And then we built a similarly decoder. This will be our size of decoder. There is also going a bigger like multi-head attention. This will be have a few mathematical expression than our normal feed forward network. And basically then the multi-head attention will be provided over there. Then we have output embedding and position encoding in this layer. So basically this is just a kind of one layer. I stacked 6 layers of these. Each is consists of 2 sublayers, like this is one sublayer and this is another sublayer. So after I stacked 6 layer of these transforms in as encoder and 6 as in decoder. So, and by using this, we achieve those results. Talking about the data set after cleaning and achieving everything, uh, I think the organization provides us around 21,000 phrases, but that consists of noisy phrases, repetitive phrases, and some empty phrases. After removing, what we did is we used 8,000 phrases for train file, 1,000 for test, and 1,000 for validations. And finally, sequence to sequence model achieved 21.5 and transform model achieved 20.8. So that was kind of small overview of our project, and the detailed mathematical expression, the tuning parameters and other things will be presented in the paper. So thank you, everyone. Any questions?
This is really interesting. Thank you so much. Unfortunately, I think we have time only for 1 or 2 short questions, but we could discuss it because the idea was to stick to the schedule to talks of 15 minutes plus 5 minutes for questions. But I think that we can save more longer questions for the discussion in the end. So does anyone have 2 short questions? So if this means that no one does, I have a small question. Could you tell me a little bit about what specific problems did you? So this transformer is a generic model for machine translation and for other applications. But did you stumble upon specific problems that are specific for the language you built a translation model for?
Yeah, this transform model is kind of generic. So apart from machine translation, it is also used for image captioning and other natural language processing tasks too. So basically, transform model only is a kind of mathematic expressions, like how we are combining a few sigmoid equations, other transform equations, and that structure I showed it. Every part has a mathematical equations, and the combination of those equation is uh, called transform model. And using those transform model, those equation are able to capture context, are able to understand the word actual English words, and then we use then we found in these application to use in machine translation. So this is kind of generic, and of course these have other applications. The problem what we faced is we were having a kind of too small data set, like for a good particle, like for we can see the state of the art results for German to English translation that they achieved a blue score of 29. So we were only backed by the number of phrases. So in future, when CDLI will be able to provide us more phrases, I think we can achieve much better results.
So we have a question from Christian Charkos in the YouTube stream. So in the Sumerian setting, we normally face massive sparsity issues. Do you perform qualitative evaluation?
Hi, Christian. So yeah, we also face sparsity issues. Of course, the data set was small and things were noisy. We also perform some qualitative evaluations like the other rhetoric score. Of course, blue score is not also that much of reliable. Blue score has also limitations. We are performing more quality evaluation and will be showed in research paper and our other things. I just give a small overview. We performed much more than this.
Okay, thank you so much. We need to go to the next presentation. Vishal, it's your turn to tell us about your experiments on computer vision.
Okay. Hello, everyone. So my project was OCR for Cuneiform RGB images, and my name is Vishal Tamlarasan. My main mentor was Jayant Jaiswal, and Ilya Kate and Emily helped also with the project. So the main tasks of the project was to segment line segments out of the cuneiform character images and map it to the corresponding translated text line. So we have both a cuneiform image and we have a translated text. So we have to map individual lines to their corresponding translated text line. And the next task was on the cuneiform image, detect and classify the individual cuneiform characters. So previously work has been done on these three papers, as you can see. And most of these works involve the use of 3D models. Now, 3D models are like, they require specialized equipment to extract these 3D models. And those would require specialized software and a lot of setup of lamps and cameras to extract this 3D model. And another issue is that these papers only work on 3D datasets and won't work on 2D or RGB images. So, so to tackle this issue, I mainly worked on RGB image. I worked on RGB images, and CDLI has a very large collection of RGB images. I think about 50,000 plus images are there on CDLI's site. So now I'm formulating my task. I went with two methods. One was a non-learning based method. Ad hoc, it uses traditional image processing techniques, and another is a learning based learning based techniques. That's like machine learning or deep learning based techniques. So this is line character detection using non-learning based methods. And after a lot of research into OpenCV methods and traditional image processing techniques, I came up with this is my final plan, final pipeline. So I give the cuneiform image. I extract the obverse and reverse views using largest connected contours, connected contours, and then I perform HED on the image. HED is a edge detection model which performs image-to-image prediction, and this addresses the canny edge detector. It's an improvement of it, and it applies semantic understanding of where the main edges of the image are. So basically, all these small edges you can see of the real image where the characters are, those will be generally ignored, but the main edges, the outline of the tablet and the line indentations will be found out. And then on this HED image, I binarize it. On top of that, I skeletonize it. Skeletonize is like the foreground pixels of the white pixels are eroded, and a basic the skeleton of the body is found, maintaining the structure. And then on top of this, I found out offline transform. It predicts a collection of lines along the skeleton of the structure. And then I find the clusters of the lines that are falling in the same cluster. And I find the centroids and then draw a straight line. So now this is for character detection. A similar method uses, I apply a morphological filter onto the image, then I binarize it, and then I apply largest connected components method. So as you can see, for this measure, for this image, it performed, at least in the detection part, it performed relatively well, showing the connected components. But one problem is that we have basically no idea which character is which. I mean, like which character, like whether this character is classified as letter A or letter C, KL or as such. And now this is for a cuneiform image without any line indentations. Now, if there's line indentations, these connected components will overlap with the line indentations, and it will completely change the image, completely change the result. So there's basically no way to understand what to separate between each of these characters, and how should we classify them. So I'll tell the limitations. So it performs for the line detection part, it performs really good on tablets which have good line indentations, similar to this image. But it fails on tablets which have a lot of curved lines, or which have a lot of cylindricity to the tablet shape. So it'll fail on that. And then with tablets on line indentation, it does not work because there's no lines. And for character detection, as I said previously, these are the issues. Now I move on to learning-based methods for line and character detection. So I task this as an object detection and classification task, where we have to detect the lines and individual cuneiform characters and give them a class name. So I do not use any language model for the cuneiform script. That means that relations between certain characters are not taken care of. Zipf's law is not taken care of, like the uh, histogram of the characters. So for example, in English, the letter E appears the most, I think. And similarly, A and IN as such are higher, whereas letters like Q and rally appear, have lower distribution. So a language model is not taken care of. So for example, over here you can see Lugal. If a language model was taken care of, Lugal, if the detector model recognizes a character that looks like Lugal as Luk Kisal, because Gal and Kisal look somewhat similar. Using the language model, it will think that it will correct the detection as Lugal, because it has a huge collection of translated text that contains these Lugal words. And similarly, like if the detector model detects two letters, let's say two words, say the together, using the language model, it'll understand that the usually don't appear at all. So it will give a correction either, or it will give a negative score for the prediction or for while training. So no language model is taken care of in this method. And now, yeah, so most of the state-of-the-art object detection and classification models are supervised learning methods, and that means that they require a labeled data set. So the problem currently we face is that we don't have any annotated or labeled cuneiform images, 2D images. So to solve this issue, I created a synthetic annotated cuneiform image that looks realistic as possible using current information I have. So I used a Blender software, and this is the basic pipeline of the generation of the synthetic cuneiform image. So from online sources, I download about 10 to 12 3D models, and from those models, I uploaded them on Blender software, and then I augmented those models, like I stretched them horizontally, vertically, and then I gave them small elastic distortions, and then so that's the model preparation part. And then I prepare a sign template. So this will be a black and white image that will contain the signs on it and the lines. It's a binary image. It's not a binary image, so it's a grayscale image. And now this grayscale image, I apply it as a input texture, as a height map texture map onto the 3D model. So initially I used a displacement map, but this would require a very highly complex 3D model. And when we finally go into the rendering part, it'll take about 2 to 3 minutes to render. So that was taking too long. So I just uh, switched to a height map where it'll just basically, it's a cheat method. It'll just basically show a cheating based method that taking care of the 3D parts. So you can see all the shadows are there, and it gives a 3D feel to it. Whereas if you use displacement map, it'll actually it'll modify the model's shape. And then on top, after I apply this sign template, I apply the textures, and from the textures, I give some specularity, some roughness of the tablet, and as such, I just manually adjusted these figures to see how realistic possible I can make, and then I started generating the image. So this will be just the sign template generation. So these individual characters, I manually cropped them from the SVG line art images from CDLI's collection. So these were drawn long years back, like using some Inkscape software or Adobe Illustrator. So the 2D images were uploaded onto those softwares, and manually on top of them, each characters were drawn and then converted to a line image. So basically, you can say that these characters are real representations of the what you can say of the characters, at least the like a orthographic view of it. So these characters were then given line gradient. The line gradient is necessary to provide the 3D feel, and you can see it's going from black to white. The skeleton backbone is the whitest, and it degrades to black on the outside. So I gave them some augmentation, elastic distortion, some stretching along x-axis, and some rotation xy. These lines, I manually created them using Inkscape, and then I again augmented them both flipping them vertically, and then these lines and characters were randomly placed on these templates. So from here you can see these models. I had about 10 to 12 models, and similarly I had 10 to 12 dimensions were there for the templates, and I randomly placed the signs and lines in no particular order, just to no particular order. There's no structure to the characters placement. And then I rendered these images. It took roughly about 20 to 30 seconds to render each image. I rendered about 2000 images. And these are some examples of the synthetic images that were rendered. Now, so I tested the line and character detection on three methods. The first was YOLO. It's a real-time object detection method, which is really fast. It has about, I think, 45 frames per second while taking care, and it takes a single shot image of the test image and tries to find out the predictions. Similarly, SSD is again, it's much more faster. I mean, it's a slightly less faster object detection method. It's about 42 frames per second, and but it has higher accuracy than YOLO. So these two methods worked relatively well on the for line detection, and the results were satisfactory. But it failed on for character detection because since these are real time based, they won't perform very well on very complex structures. So I then went on with mask RCNN. So mask RCNN is a implementation of it's a improvement of faster RCNN. So it takes in like a mask of the objects during training, and it tries to find the region of proposals during this training part and concentrates on these ROPs and improves the training of the model. So I went with mask RCNN because I already have the sign templates. So basically, this is the mask of the rendered image. So using this, and since this was annotated, I had the locations of each of these characters in txt file, basically the character name and the XY coordinates of them, the bounding box coordinates of them, XY and top right and bottom left. And yeah, so since I had the mask, I went with mask RCNN as it would perform really good on this, I assume. And now for the results. So we used 978 synthetic images for training, 500 for validation, and for the initial test, 20 characters were trained on, just to see if the results were promising. So it took about 30 hours to train using the following specs: 4 GTX 1080s, and the latest versions, at least the latest versions of CUDA, TensorFlow, and Sirian. So for the synthetic images, it reported a score of 57.1% for about 500 test images. So at this point, I just stopped the training and then went on for testing on the real images. So now the problem was that to find a test score on real images, I don't know where the characters are located. So I manually annotated the real images just for testing purposes. So when I do the MAP calculation, it will do a bounding box overlap from the tested to the real, and it will find the score for that. That's how MAP works, and it reported about a 22.1% for real images. Now, the score was brought down heavily by false positives. So for basic characters like 1dis, 1u, and a, some of these characters like form the building blocks for other very complicated characters like 8dis and 1u can, I think, for TIL, it can form a building block for that. So there was a lot of false positives where these characters brought down the MAP score. So generally, complex characters like SEZ3, NA, LA, GAL, TIL performed better for the MAP calculation, while 1U, 1dis performed lower. So, okay, I'll show you. This is the results for the line detection. So in this case, compared to the non-learning based methods, it takes care of curved lines better, and it has better score also. And these are some of the results for the character detection. So as you can see, LA is properly detected. Mind you, this is only for 20 signs, so only 20 signs shown. So many of these characters are not trained on already. So LA is found properly, NA is also found, ZE3 is found, and then here you can see 6 Gesh or so also found. And then again, you can see these one disk characters getting a lot of false positives because some of these form the building blocks of these, like for example, 3 disk. No, no, sorry, not 3 disk. 3 disk is over here. And you can see also 1U also creating an error over here. Now, so I was checking for improvements. So one improvement I thought of is cycle GAN. So this is a paper implemented about 2 years back, and so the basic idea is it has a synthetic image. It tries to synthetic image or synthetic video. It tries to apply a domain adaptation from say the synthetic to a real, and it tries to use the real domain informations like background color, background texture, the specularity, the reflection, the shadow, the volumetry also. So it tries to apply those domain information from real images onto the synthetic images videos, and then it tries to improve the detection after this. So I'll just show you from this. Yeah. So this is an image from GTA 5. So as you can see, so when they did the detection, they got a reasonably good results. But when they applied domain information from real image, this is a real image. When it was applied on this GTA image, it showed improved results when it was finally passed on to the character, passed on to the model detection and classification. So when I found this, I thought that maybe it will it will improve the results for my character detection on cuneiform images. But sadly, it didn't show any improvements. In fact, some of the cases it lowered the scores, because I think the structure information is lost a little bit. As you can see from these, the highly detailed structure informations are kind of lost, whereas the overall structure is maintained. So maybe these degrade the quality of the detection. And yes, so the basic ideas from this is that the domain knowledge, like say the texture, the shading, wherever the light lamps are located, those don't matter much. And now this is just I try to improve the data set using 78 characters. I gave them more augmentation, and there was a slightly increased MEP score of 26.4% compared to the 22.1%. But again, a lot of false positive appeared for the numerical characters. So judging from the conclusion from this and the former one, from the cycle Sakada method, and from this, I judge that the domain information is not more important for character detection, whereas the basic structure of the character is more important. So we need more robust methods of creating the wedges of the cuneiform characters to improve the training. Also, I believe that I should increase the training size of the dataset. And one possible idea of creating these robust methods of augmenting these individual characters of the cuneiform characters is this is a recursive radial package language. So this was applied in the Chinese language. So basically, a model structure is like this, and a little more complicated method is the background. You can see the silver color. So it tries to build, you give a basic code to this, it builds a line like this and give this code, and you can combine these codes to convert more complicated characters. And again, these complicated bases can be finally formed into real characters, real words. So and so some of the characters are formed over here, and on top from these characters, pix to pix, the paper applied a pix to pix methodology that's similar to cycle GAN, where it changes the domain information. So some of these characters were created to somewhat realistic looking. So basically, these basic structures were converted to realistically looking uh, Chinese characters that looks like a white chalk on a blackboard. So if a method can be developed for cuneiform character, I believe that more augmented cuneiform characters can be created for the training, and the model will learn better. So yeah, so these are some of the improvements. So my next task will be for making a live demo where you upload the real images and it will output the character detections and line characters, line indentations. And that's all from me now. Questions?
Thank you so much. This is very impressive, but unfortunately, we have run out of time. So I think we will have questions in the during the discussion session. So,
Okay. Thank you.
but thank you. It's really impressive. Now we will have to switch to to the streaming. So just in case you don't have the stream open, I will those of you who are in Hangouts, I'm sending the link to the chat. So let's mute the audio here and go there uh, and wait for the beginning of the video.
Hello everyone, welcome to my presentation. In this presentation, I would be presenting my project Multi-Layer Annotation Query Tool. This project was developed under CDLI during my Google Summer of Code 2019 program. About myself, my name is Sagar and I was selected in Google Summer of Code 2019 to work with CDLI. Coming back to my project, Multi-Layer Annotation Query Tool. First of all, what are annotations? Annotations are metadata that is attached to our original data which provide extra information about it. For example, we have a sentence like Apple is going to buy a startup. We can have a part of for every word in the sentence we can have a part of speech. This is a type of annotation which we provide to every word in the sentence. So what is multiple layer of annotations? It's just having more type of such type of annotations. For example, in the same sentence, Apple is going to buy a startup. We can have one more type of annotation, that is named entity tag for every word in the sentence. So for like Apple is a company. So in this sentence, Apple refers to a company. So we have the NER tag for the word as organization. NER basically NER tag is used to tag every words that are like organization name or person name or a location. So we don't have any we neither have any organization name other than Apple or location here. So all other tags are tagged as other. So why do we even need a tool for like searching over these tags? We can always use a normal text search which you have in our text editors. Yes, for basic searches it's fine. Like if I want to search for verb, like in this example, if I want to search for all the words that are verb, then we can easily search and we'll get all the words that are verb in the sentence. But there is an issue with this. What if I want to query for 2 or more words, continuous words or even non-continuous words? Then a normal text search won't work for this. Now we can use regular expression for this. Like if I need a verb immediately about a pronoun, then we can search it using this regular expression. But as you can see, just for the small query we have to write this much complex regular expression, and it would get complex a bit later. Also, we have some other issue. What if I want to query over the semantic tree? It's not even possible with the regular expressions. so we need a tool. I would have already like convinced you that we need a tool for this, but there are already, but you might be thinking that there might be already existing tools for doing this task. Yes, we already have a tool named ANIS, which can be used to query over multiple layer of annotations. It uses a language named AQL to query over the complete corpus, and also it visualizes the results which we get. This is a screenshot from ANIS tool. On the left, on the left of the image, we can see that the query writer part where the query is written, and on the right the results are shown. But ANIS still has some limitation. And first of all, the limitation is it uses a language named AQL, which is a completely new language to learn for everyone. Also, the query generator, the GUI which can be used to generate the AQL query, is a bit complex and not intuitive for non-technical users. So we came up with a tool, CKP for RDF. CKP for RDF can be used to query over multiple layers of annotations of our data. It uses CKP language to we use CKP language to write the query. CKP also CKP is the language which is used by is a widely accepted language to query over the corpus. Also, our tool CKP for RDF has a query generator GUI which is quite intuitive and easy to understand even for non-professionals. This was the query writing part. Now, when we come to retrieval part of the data, we use SPARQL. SPARQL is used to query over the RDF data. The RDF data and SPARQL are quite widely accepted tools to query over the graphical data. So basically, CKP and SPARQL both are the highly accepted tools in both their fields. Also, in our tool, we specify this. We can using the query generator GUI which we have to generate the query. We can specify the dependencies between the words, like whether one is the head of another in the semantic tree or not, as the parent or child. Also, we can specify the proximities, like the distance between the two words, whether they are like adjoining words or like we have 4 words or 5 words in between. Also, our tool is highly configurable for any type of data set. How ANIS is basically better than ANIS. ANIS, first of all, we use the CKP, which is already quite acceptable among the linguistic to query over the corpus, whereas AQL is completely a new language to learn. Also, we have a query generator GUI which is quite intuitive to understand, which is quite easy to understand and can be easily used by non-technical users and in order to get the results. Also, as CKP and SPARQL both are the best of the worlds, CKP for RDF bridges the gap between both of them and bridges the gap between best thing of both the worlds. But we still have some limitations of CKP for RDF. In order to increase the power of the tool, we broke one of the constraints of CKP, that the two tokens should always be specified one after each other would always be continuous. We broke this constraint, and now the two tokens don't have any by default dependency in between them. Although this was done in order to decrease the complexity of the GUI and increase the power of the tool. Although this process for this task we have to specify, in order to make them continuous, we have to specify a dependency between both of the words, as you can see in the lower example. Also, one of the limitations is that although this task has been automated using in the GUI, in the query generator GUI which we have, it already automatically adds a dependency between the two words. Also, one of the constraint, one of the limitation is that it takes more time when after we have broke the constraints. Our approach of doing the project, my approach of doing the project was first of all to completely convert that data which we have into the RDF format. After converting complete data into RDF format, the graph was built from this these RDF files using the CKP server. Now CKP for RDF tool receives the query in form of CKP, and these CKP queries are converted into SparkQL queries. This query is processed, and this SparkQL query is used to query over the CKP server. SparkQL queries over the CKP server over the graph which we have built in the CKP server. My contribution in the project was first of all to complete the complete data from CDLI kernel format to RDF format. Also, the complete query generator GUI was built by me. Also, the app has been made highly configurable for any type of data set which we have. Also the tool has been dockerized, and it's easy to and is now is easy to deploy over any server. Also, the tool has been integrated with the CDLI framework, so it can be directly accessed from there. Also, we have deployed the tool at the given link, and it can be accessed from there. The tech stack which we have used is SparkQL in order to query over the graph, CQP for when I use as a query which is generated using a query generated GUI. Flask is used to handle the complete backend part, and Flask is backed by Python. JavaScript and jQuery were used in order to make the complete query generator GUI which generated the CQP query. Also, Bootstrap, HTML and CSS were used in order to beautify the complete web page. Now these are some screenshots from a tool CQP for RDF. This is a screenshot of for Word. We have two sections in a CQP for RDF tool. That one is for words, which we specify all the words which we can have in a sentence, and another one is for the dependency, which specifies the dependency between all these words. So this is a screenshot of a word. As you can see, the top section specifies the complete query which we have for a particular word, and the toolbar which we have, scroll bar which we have, specifies can be used to change the change how many times a word would appear, and specify how many times it would appear. Also, we can add more properties. All these properties will be added in AND using the AND property button. And when we have these properties, we can add more properties using OR. And all the values which which you will be seeing in the drop down and this value below them are can be easily configured using the config file which we have. Now this is the dependency section. Dependency section. This is the specified dependency between two words. For example, here we have this dependency between W1 and W2. W1, along with W1, we can easily also see the complete query which W1 has, and the in the second drop down, that is like shows the dependency between the two words, like whether W1 comes before W2, or W1 is a parent of W2 or child of W2, and we can all these values are can be specified and are there in the drop down. Also, we can then specify the proximity using the proximity between the two words, like whether they are in the particular range or they are adjoining. This can be easily changed and using the drop down which we have for like which you can see of range. This tool can be used by corpus linguistics in order to query over the large data, and also it can be used by various historians in order to query over the CDLI database, which is a big database. Future plans for this tool is to make it more generalizable and automating the complete data upload. Currently, the data has to be uploaded manually over the Fiseki server. If this process could be automated, in future we are planning to automate this process. Further, we also plan to have an admin portal where all these where we don't need to specify everything in the instead of specifying everything in the config file, we can specify everything in the admin portal only on the GUI. Also, after the GSOC project, we would be writing a search paper for the complete project. The complete team for the project I was a developer, and Max and Ilya were my mentors, which helped and guided me a lot. Yeah, that's all for my project. Thank you.
Thank you so much, Sagar. This is an impressive work that I personally like very much. We have time for one small question, or maybe two smaller ones. So if no one has questions now, oh no, there is one in the comments of the video. Yeah, it's just Christian Charkos first says that it's a nice presentation and very nice work. You should listen to him. He's someone working on multi-layer annotations for about 15 years now, and he's very curious to learn how our serologist colleagues like the interface. Is there any systematic feedback collected so far? And maybe there are some remarks from people who will actually work with it.
Yeah, like we haven't had any asked anyone like the review was done by Emily and Ilya only and Max, so not anyone which is working in that field exactly. Yeah.
But just to make it clear, this is applicable. This is very highly configurable, and it can be applied to basically any other corpora which are in Conal RDF. So I guess if there are no any other questions, we can move to the next presentation, which will also be a video. But yeah, if there are any more questions. Okay, then let's go to the next video and maybe we will discuss more in the discussion section. Please return to the streaming, to streaming.
Hello everyone and welcome to this presentation. This is Aman Iqbal, and in this video I am going to give you a brief overview of my Google Summer of Code 2019 project. So without any further ado, let's get started. To start with, let me give you a brief overview of the circumstances which led to this project. As you might know, CDLI, that is Cuneiform Digital Library Initiative, has a very large collection of geographical and temporal data of artifacts at its disposal, which is only present in the database. So there is a need to show a high level overview of those information in forms of some stats and the visualization or in any other way to our users. So this project aims at creating a stat page which gives overview of the stats or the statistics of different columns in any specific table, and also 6 different visualizations which were developed in d3.js. Moving ahead, these were the 5 main objectives I accomplished this year during GSOC. First one is I created 6 different pluggable visualizations for the search results. Pluggable in the sense it is developed in modules so that it can be placed anywhere we wanted. Second one is I integrated visualizations to the advanced search results page. All these 6. Moving ahead, the third one is I constructed a general stats page to give a high level overview of the stats present in any specific table in the database. I also updated the UI of the framework, decided during the community bonding period only. I also documented the entire code I have written so that any other newcomer can contribute in whatever way he could without facing any difficulties. And I also added appropriate no script fallbacks. I will explain about this in my upcoming slides. Now let me show you the results which I got at the end. So yeah, this is the stats analysis page. This gives a review of the selected table. Okay, using this drop down, this drop down lists all the tables present in the database, and by selecting any of them, you can see this table. Like you can see the information about the column name, which all columns are present in that specific table, what data type has been allocated to them, what is the length assigned to them, the number of null values that specific column is having, the number of distinct values that specific column is having, the maximum value or length if it's a string that column is having, and the minimum value or minimum length of string that specific column is having. So for integers, ID, author ID and artifact ID, again the maximum and minimum value is going to be integers only. For date, data type is date, time, and again there is nothing like length for dates. Number of null values is 0, number of distinct values is 2080. Maximum value in case of date is the most latest date, that is 19th of February 2019 in this case, and the minimum value, that is the oldest date present in this date column inside this credits table is 4th of December 2001. Similarly, I have shown the information about comments and credits too. These are of type string, and you can see maximum and minimum value, that is the maximum and minimum length of the strings in these two columns are 0. That means both of those columns are empty. I mean, all the rows in those two columns are empty. And at the end, I have shown how many rows this selected table has in our database. After that, I developed the bar chart. This shows the languages in the x-axis along with the count of artifacts in which this language appeared. And again, of course, this is an image, so you cannot interact with it. But in actual visualization, on hover over any of these bars, you can see the information about what is the actual count of artifacts. With this specific language again, and you can see this scale over here. This is logarithmic, so you cannot actually predict what these values could be. But yeah, this gives a basic overview which you can, using which you can get precise information on hover over any of the paths. After that, I developed the donut chart. Again, on hover over any of these arcs, you can see the exact value of the count of artifacts which were found in that language. And I have shown a legend over here which maps the language name to the color so that you can identify which arc corresponds to which language. After that, I developed the radar chart. This gives a high-level overview of how a specific genre, how the number of artifacts found with a specific genre is distributed with respect to the regions. Here I have shown top 6 genres along the axis of the radar chart, and with respect to the top 3 regions. The count of artifacts found in that region, categorized by that. After that, I developed the line chart. Here again, I took periods in the x-axis and the count of artifacts found in that period along the y-axis, categorized by the top 3 genre in this case. Okay, using this drop down, you can select which combination of categories you want this line chart to display. Currently, we are having period versus genre, period versus language, and period versus materials. In each of the cases, I have periods in the x-axis along with the corresponding count of artifacts of that category. And again, this legend corresponds explains which of the lines corresponds to which specific genre in this case. After that, I developed the dendrogram chart. This gives a kind of tree-like structure of how a material or any other attribute which is kind of nested in terms of parent, which are related as a parent-child relationship, which are related with parent-child relationship. So in this case, I have displayed materials. Material is categorized into stones, metals, bone, and clay, and it is further categorized to these specific values, which I have shown as bar chart. Again, here you can see stone is also categorized into quartz, which is further subcategorized into flint. And on however any of these bars in the actual visualization, you can see this ball at the top showing the corresponding count of that specific material. Count of artifacts in which that specific material has appeared. You can also guess this count via the scale at the top. It's linear one here. After that, I developed the choropleth map again for two different. In terms of two different values, that is proveniences or sites and regions. In this case, as you can see, currently we are having around 317, I guess, different proveniences or sites. So in this visualization, I have shown where each of those sites are located in our world map. Again, it's an image, so you cannot interact with it. But in actual visualization, on hover over any of these small circles, you can see the name of the proveniences along with the region. And again, as you can see, like it's categorized on some basis, like deep blue dots appear here, then light blue here, then something kind of white here. All of these are categorized by the region. And you can see the zoom in, zoom out, and reset functionality on this world map. So you can zoom at any level here, and you can interact with the map. And again, you can filter this map by regions as well, so that it will show you the region information of the regions we are currently having in our database. Yeah, now after that I integrated all of my 6 visualizations to this advanced search results page. As you can see, like, and on clicking on any of the bars, on any of this links here, the corresponding chart is okay. This is a snapshot of the advanced search results page. So depending upon your search queries, these visualization which will only display the information of those artifacts which were returned as a result of your search filters. Currently, these search filters were having some problems, so I have just displayed all of these. All of my separate visualization which I constructed earlier over here. Coming down to the strengths these visualizations have, my project has rather all of my visualization which I constructed are responsive with respect to screen sizes. So with respect to device screen sizes, so irrespective of you view them on tablet or mobile phones or laptop or desktop, it's going to appear fine without any kind of breaks or something like that. I've also added fallbacks, that is no script fallbacks for users with JavaScript disabled. That means if for some reason the user has disabled JavaScript, then I am showing a fallback image of the visualization. Like this is how the visualization would have appeared if you would have JavaScript enabled. And also I have a basic friendly text below that image saying please enable JavaScript to view the actual visualization. And I also have the selection of attribute combinations in some ways visualizations like this line chart you can categorize by in 3 different ways, and also the choropleth map by proveniences and regions. And the most important thing, I developed all the codes in a very modular and generalizable way, that is it can easily be generalized to any other attributes apart from those which have been tried here. Yeah, there are some limitations too which could have exploited, like again whatever the database queries I have written can be optimized with respect to time space trade-off. Like again information about a small table can be stored in form of some data structure like hash table or something like that, and so that in further queries, if the information about the previous table is required, so we need not access the table time and again. We can just use the value I have stored in a hash table previously. Okay, in PHP it's associative array. And also there are some attribute combinations I have not tried, or some attributes I have not tried. That is themes, composites, authors, rulers, dynasties, etc. Those can, those can be tried in the future. And that's not going to be difficult since I have my code in very generalizable. I have written the code in very generalizable way. Moving ahead, the ways in which this can be used is, some of them are like, again, any of the visualization provides a very clear and quick understanding of the artifacts related information in a very appealing way. It also makes large amount of artifacts data currently present in our database very much understandable to the user. Like currently we are having around 3,34,540 artifacts information. But again, no one can just go through the entire database, even if they are given access to understand anything out of that. So there is a need to show those statistics to our users in some way or the other. With that, also the highly correlated parameters can be identified. This project will also aid CDLI in garnering interest from researchers and academics. They can come over here to get to know about archaeological and artifact related information in a better way. And again, as you can think, visuals provide a very easier and quicker ways of comprehending the data, and it also provides the remembrance of the statistics for a longer period of time. My future plans are as follows. Like, I plan to try out different attribute combinations which I have not tried so far, and tune my project in some way or the other. And I wish to be a long time contributor to CDLI, as generally I love to do open source in my free time to expand my skill set mostly. And I also wish to mentor CDLI in future open source events, like Google Coding or maybe Google Summer of Code next year, if given the opportunity. And yeah, definitely after that, I will also be there with any other help or suggestions I can on any of the domains, on any specific domains in which I have knowledge or expertise. And yeah, overall my experience was really amazing. I had very helpful and supportive mentors who have always motivated and encouraged me in improving my work so that it could be helpful and beneficial to a large number of CDLI users. I also learned the practical implementations of some data structures like hash tables to manage the time space trade-offs, and I could see the effects for the same, like how it actually benefits or how it actually minimizes the time complexity in some cases by what do you call, by sacrificing some memory. And yeah, definitely I increased my familiarity with D3GS a lot. I was not very good at the same previously, but this project made me understand it in a much better way. Yeah, and at the end, I would wish to say thank you to all my mentors, and thanks a lot to you too for watching this video.
Thank, thank you so much. Excuse me. Thank you so much, Aman. I think this is very helpful and it looks amazing. So we have some time for questions. Does anyone have questions? Yes, and I wanted to apologize for technical difficulties. The link to the slides will be below the video after streaming, and uh, and uh, and actually, but I expected more technical difficulties to be honest. So
Yeah, I mean, no problem. Actually, what do you call? We can post the link to my video in the chat only. Like it's, I guess, Emily has already uploaded it in our CDLI channel.
oh, that's right. Yes. So I will insert the link to that video too. Yeah.
Yeah, yeah.
So questions? So if there are no questions, that then maybe could you extend a little bit, talk a little bit about how did you choose the specific queries? Why did you choose ones of, or why did you choose these exact things to represent? How did this process go?
Sorry, can you please repeat the question?
Uh,
Like,
I,
what?
I was wondering, how did you choose the specific queries that you've represented on the with these very nice visualizations? Why did you choose these ones?
Okay, I mean, actually, I have used MySQL queries to what they call retrieve data from the database, and yeah, and after that, I just send that information from our model to the controller, which then what they call sends the data to the front end or the view, and yeah, I guess yeah to the JavaScript, and the JavaScript renders that what they call it, the entire data sent from the, I mean, processed from the model itself. I mean, okay, model, the basic workflow is the model retrieves the data from the database using MySQL queries. And yeah, as I mentioned, like it, it matters how you write the queries, like how you perform the join, or you access it separately and use some concepts of like hash tables and all to avoid accessing the table time and again. And then after that, what do you call? I process whatever data I retrieve from the database in the format which my visualization required. Like say suppose if the visualization like the bar chart, it only requires the count of the artifact. So I only send the name of that specific language along with the count to the controller from the model, and then the controller send that information to the JavaScript, to the visualization, basically to the view, and then using d3.js I render the visualization on the web page. This is the basic overview of how it works.
Okay, thank you. And Emily could add something as she wrote in the chat. Could you please?
Yeah, so actually, Aman prepared a very nice survey, which we distributed among a couple of seriologists to decide which visualizations were could be the most useful, and also we started exploring which associations we were interested in. And along the way, Rune and I had a meeting about like which associations we should use in the graphs. And then we came back circle with Aman to make final decisions on which visualizations would be used with which data.
Okay, that's very impressive. So it is motivated by theoretical research, not just some random ideas. It is really motivated by research, which is very impressive, I think.
Yeah.
Okay, now it's time to go to our last presentation, which will be screen shared in Hangout. So don't go anywhere. It will be about TI conversion of the CDLI data. So Ralph, please, it's your the stage is yours.
soon as I can find my slides. Sorry, there we go, there it is. All right, so hello everyone, I'm Ralph Giles. I did a project on converting the CDLI's transcription data into an exportable format. It was part of the Summer of Code. Willis Monroe was my primary mentor, but I also had help from especially Emily and the other mentors in the program. So as I'm sure many of you know, the cuneiform digital library is a large collection of cuneiform inscribed objects. There's almost a third of a million of them. And about a third of those have digital transcription data. So that means the database has a copy of that somebody's entered of what the inscription says, either in the original language and some of them have translations. So it's a central resource for scholars. The transcriptions, the interface currently looks like this. So you can enter information here where you want to search. And then when you select a particular tablet, it will show you, sorry, is there a way to get rid of the echo? There's metadata about each object. If there's a photograph or a hand transcription, it'll be shown here as an image. And then there's a transcription here. So this is the transcription data that I was working with. So there's going to be a hang on. Sorry, I can just hear myself talking on a delay, and it's really confusing. I need to mute the other thing.
Probably mute the YouTube stream.
Yes. Sorry, you told me to do that. Okay. Sorry about that. So there's a transcription of the cuneiform, and then some tablets have a normalization where it's converted to Latin letters and or a translation into English, German, or another language. So the transcriptions are stored in a custom text-based format. It's called ATF, I assume for ASCII transcription format, but I'm not sure. So there's an object ID, oops. So an object ID, a reference, what language it's in, annotations of where on the tablet it is, and then we have the transcription data and the translations. So this is the format it's in the database, and when you go to the CDLI website, you can download this if you want to work with it. So that's good for specialist import and exchange, but it does require specialist tools to work on it because it's a format that's only used by the cuneiform community. So our idea for the project was to use a more widely recognized format. There's something called the Text Encoding Initiative, which for the past 25 years or so has been used by the scholarly community and mostly in other languages for historical and ancient texts. So it's a way to digitize the text and then mark it up with various kinds of annotations. So it looks something like this. It's an XML language, so it has angle tags just like HTML. So you have a text which has a body, and there's an addition which is divided into parts. And then you would have a line with a line index, and then each word can be marked up, and you can add additional annotations here. And so the idea was that this is a more popular format, more digital tools can read it and access it, and there are nice viewing environments for it. So we wanted to make the CDLI's database available for people who want to use those tools. So the core of my project is I wrote a conversion script in Python called ATF to TEI, which takes an ATF record in the format that comes out of the database and creates the XML file in the Text Encoding Initiative format. It uses the PyOrac parser, which was an already written parser in Python which interprets the ATF and builds a syntax tree, and then we walk the syntax tree and output an XML version of it. Now, to make the text accessible, there's a standard called canonical text services, where it defines a layout where you group the texts into groups, and then you put them in a file system hierarchy with annotation data so that the author and the title and things like that can easily be found. And then there are established software, server software, which will make it available online and hyperlinkable, and then the viewing environments can read it. So each text is assigned a universal resource name, which can be used for citations. And there's a project called Capitans, with its clever name for CTS, which provides guidelines for formatting these and has become the de facto standard for how you lay these things out for ancient texts. And they provide tools, including the server software that we use and validation tools as well. So on top of my ATF to TEI script, I wrote an ATF to CTS program, which can take a whole series of ATF records instead of an individual one, and then convert them one by one in parallel. It adds the correct metadata like the universal research name and builds the index files that are needed for the CTS hierarchy. So with those, it can be served using the standard tools. And then that takes sort of any collection of ATF, but specifically for the project, we wanted to export all the data from the CDLI itself. So I wrote a further script called CDLI to CTS, which wraps CDLI ATF to CTS. So it loads the CDLI database export, which is published to GitHub, and the catalog metadata, and then you can filter what it produces based on specific CDLI IDs or specific values in the catalog metadata. And this script can convert in running in parallel on my laptop the whole database in about 30 minutes, or just a few seconds if you have a small subset of records that you're interested in, for example, for a specific publication. So this is now running automatically in a Docker container on a server provided by Compute Canada. So every night, the official CDLI site runs a database export, which extracts all the ATF transcriptions and the catalog metadata and uploads that to the CDLI data repository on GitHub. And so my container will fetch that data from GitHub, run CDLI to CTS on it to create a new set of CTI files, and then it will upload any changes to a CDLI CTS repo on GitHub. So now we have live export, not just of the ATF data in ATF format, but also of the CDLI data in the CTS file hierarchy using the TEI. So once we have that, I set up another container that runs the Capitan's Nemo and Nautilus servers, which are Flask packages that also run in Python. So it's the same package that Sagar used for his things. And so this serves the TI transcriptions over an API, so they're available to people who want to cite them or download them into their Python notebooks or anything else. So that's everything necessary to make the data available for reader software. And so, for example, there is a new reader called Scaife, which was written for the Greek and Latin community, but they want it to be useful for other languages. And so I set up a demo of that, which will let you load cuneiform texts and look at them just like that. So here I can try and switch around. This is a live demo. The link is up here. I can paste that in chat later. But basically, when you load the page, it fetches from the API server a list of documents that are available, and you can filter these to limit what's available. And then when you click on one, it will load the text. So this is a transcription of the cuneiform text, and you can pick different ones. And then if there's a translation available, it will also show that in parallel. So that's just a demonstration of the live data being served over the internet. And that's it for my presentation. Thanks everyone for listening. And do you have any questions?
Thank you so much, Ralph. This is very neat and very nice. I like this.
Thank you.
So then I have. I know that Skyfield provides a lot of possibilities. For instance, comparing different editions for the same text. Are you planning on integrating this as well?
Yeah, I would really like to do that. It's fairly easy to add things there. This viewer setup is actually a framework that the Skype people did, where you can add different readers and different annotation tools on the side. But these are the only ones I had time to hook up during the project. But it's very easy to add things where you have a parallel reader. It would also be nice to be able to, like, this does side-by-side translation, but for a lot of the texts, when they're wider, it would be nice to have interlinear so it fits on the screen better and things like that. The other thing I really like about Perseus, like this is the Greek and Latin site where you can just browse through their catalog and pick something to read. And it's a little slow to load sometimes, but one of the things they have is you can click on a word and it will give you information about the words. So right here, there's the morphology. They have, for Greek and Latin, they have an automated limitizer, so they can tell you exactly what form it is, which is really helpful as a student when you're learning, and it can show you commentary and things like that. So I'd really like to have that available for the cuneiform texts as well.
Yeah, that would be really good. So there's a question, actually 3 questions from Christian Chiarco.
Oh, okay.
The TI expert only covers transcription data. Any ideas about metadata and annotations? This would require composing non-ATF data.
Yes, so the Scaife people want to add GraphQL query backend to the project so that you can load annotation data that's not in the TI format. So some of the things like the tablet metadata and the stuff that's already in the catalog, we can add to a header of the TI file, and then the interface could load that. But the long-term plan is that they will have a GraphQL query backend so that you can put annotation data in whatever format you have it, and then the server, the Scaife server, will pull that all together and make it visible in the viewer.
Yeah. Thank you. So, does anyone else have other questions before I go to the second question of Christian Chiarcos? Okay, then I can proceed. So, is the CDLI TI schema comparable to the ETSCL TI schema?
I don't know, because I don't know what the ETSCL schema is, so I will have to look that up. Sorry. I just tried to follow what Orac had done. They've done some experimental TI export of their own, so I mostly copied their schema, which, as far as I could tell, wasn't formally defined. I just tried to make my document look like theirs. I guess one difference is I laid mine out in lines because I think that's more what the ATF shows, and they did things as continuous prose with just milestones marking where the line breaks were. But otherwise, I tried to make it look as much like theirs as I could. Oh, for Sumerian literature, that sounds excellent. I'll have to look at that. Thanks.
And also, there's a question about did you use Roma/ODD to generate a custom TI schema?
No, I just the schema is kind of done by hand. I generated I convert the parse tree from the Orac parser into a set of documents, and then I serialize themselves as valid XML, and then I just checked that it passed the Capitan's test suite. So they do some basic validation according to either the Epidoc schema, which is the one that I used, or an older TEI one.
Okay, yeah, and I also have a question. So as far as I understand, TI and CDS or DTS are mostly compared. So they are mostly created for static resources, and as far as I understand, the data in CDLI is being processed and updated with new or alternative annotations, if I am correct. What do you? Is there any versioning or like releases for the data? Not I don't mean not review, but some milestones that you probably form as releases on GitHub or something like this. Is there something like that?
So right, there's several tensions between the way the CDLI data works and the way traditionally TEI has been done. So the CTS guidelines, the original vision was that the universal resource name would be versioned. So there's a version field you can put in there, and when people were hand digitizing text, whenever they made a major new addition, they would bump that number, and so they show up as different documents, and you should do comparisons between them. But for my conversion, the only versioning we have is the version of the GitHub repository that we upload the changes to. So you can check out different versions if you want to look at them as a scholar. But as far as what the reading interface gives you, it's just whatever the server has been updated to. I mean, in theory, you can put a change list and whatever in the TEI header, but I don't think that's very useful for machine access. So I think what I thought was probably the best is just to do the same thing that the CDLI itself does and treat it as just get the latest version that you can, because the translations are being improved all the time.
Yeah, that makes sense. Thank you. So I think it's time to go to the general discussion and closing remarks. So first, I think that since we didn't have time for questions to Vishal, we could start with that. Does anyone have questions about this character recognition and line recognition project?
I don't have a question, but I just wanted to say I think the training images for Vishal's project are really cool, and we should tell the archaeologists about them for doing their digital recreations of archaeological sites.
Hi, Rafa. Thank you. Max, I think Christian has asked one question.
Okay.
His question was, I guess the quality and types of the source images varies greatly. Would be curious whether you can identify a specific subset of images or rule that works well. So currently, like what I thought about is like using the detection and classification model, like you find the individual MAP scores for all the real images and then rank them and then find a threshold up to which it performs good, and then any of the newly tested images that fall within each of the categories you can then create, which is good quality and not good quality images, at least with the current information. I need to think about it. And another question was asked by CDLI. Somebody asked for the discussion later, Vishal. If we were to prepare a crowdsourcing interface for tagging images, how many tablets should be tagged? So currently, I'm using for my synthetic training. I'm using 2,000 images for training. Sorry, I'm using about 1,000 images for training. Now, like for testing purposes, I tagged 65 real images, and for each image, for about 20 signs. So roughly, each image had about a collection about 15 to 20 subset of my 20 signs. So it took about a while, about 5 to 6 minutes for each obverse and reverse used to make sure that each of the characters matches with the translated position. But I don't know any I can't read cuneiform script as such, so I think serializers should do reduce the time a lot. But again, this will be a huge manual process, so I'm not sure if there are people and there is time for doing that. So I believe good amount should be about 2,000 images, 2,000 annotated real images, and so each for serial cuneiform image, it has a obverse and reverse view. So basically, you can say annotate about 1,000 serial images. Yeah, that's all from the questions I can see in the YouTube chat.
Okay, thank you, and also thank you for not forgetting about these questions. I was looking for them but couldn't find them quickly. So does any
Sorry, the last part. What you meant by correct the algorithm as such? some automated process for it. Sorry, continue. Okay. Oh, I'm sorry, I didn't really understand. Can you like possibly write a question? I'm not sure what you meant. Yeah. Okay. Yes. Yes. Okay. So, I mean, like the current object detection, if you, it may give, I mean, correct or false results for the, let's say, 20 trained signs. So, I mean, it will mark the bounding boxes for the when you get the output. So, I'm not sure it and yeah, there are tools like labeling tools are there, and those are pretty easy to like use. But yeah, it will require reading from the real to translate it to make sure the positions are correct and whether the order is correct as such. So some preemptive method of identifying the locations. Not sure unless we use this object detection model at the moment, as far as I can think. Yeah.
Okay, thank you. Is there any are there any more questions to Vishal or to anyone else? Remarks? Then maybe if there are no more questions or remarks, we can proceed to the closing remarks. And Emily, would you like to say a few words about a few words on this?
Yeah, so if there's no any more questions, then I would give the final words to end this session. So first, I would like to thank all of our students for their participation. All projects were excellent, and also thank you for putting time into this final preparation after the Google Summer of Code ended. I also want to thank, of course, our mentors, new and returning mentors, who I need to mention were not paid to do this work, so it's all voluntary work. And special thanks to you, Max, and Ilya for organizing this last meeting with coping with all the technical issues. I'm glad I didn't have to do that. And also thank you, Ilya, for your support in running the weekly meetings. And again, thanks to everybody, and see you all next year.
And thank you so much, Emily, and thank you, everyone. So, if if yeah, I guess we can close the session. So I would like to add from myself also. Thank you so much for participating in this meeting, and thank you so much for everything.
Yes, it was great to work with you all. Thanks.
Same.
So,
thank you, everyone. Yeah.
so thank you, everyone. It was a nice
Yeah.
experience. The 2 months was
Thank you.
amazing. Thank you.
Thank you, everyone. It was like really a nice experience working with all of you.
Thank you from my side too.
All right. See everyone online.
Yeah, let's close this session. Goodbye. Thanks.
Ciao.